Hello friends, today's question: when a particle of mass m moves on the x-axis in the potential of the form Vx equal to kx square, it performs simple harmonic motion. The corresponding time period is proportional to square root of m upon k, as can be seen easily using dimensional analysis. However, the motion of a particle can be periodic even when its potential energy increases on both sides of x equal to 0 in a way different from kx square, and its total energy is such that the particle does not escape its infinity. Consider a particle of mass m moving on x-axis. Its potential energy is given as Vx is equal to ax 4 raised to power 4, where this is alpha, not a, and alpha is greater than 0 for modulus of a near the origin, and becomes a constant value equal to v naught for x is greater than or equal to x naught, as in figure. So this is a figure which is being plotted between the potential energy Vx and the displacement x, and it is somewhat like a, you can say, for the value which are near to the origin, the values almost increases in the both side of the plus and minus x, whereas for the values which are greater than x naught, for both positive as well as negative x naught, so this is negative and this is positive, after that it becomes constant to v naught. So this is our v naught. Okay, so we have to find out these three things. First is, if the total energy of particle is E, then it will perform a periodic motion, so we have to find out a range of E. In the second part, we have to find out the time period when the periodic motion of small amplitude A is there, and the last part we have to find out the acceleration of particle for when x is greater than x naught. Okay, it means for displacement which are at away from these values, x minus x naught and plus x naught. Okay, so in this case we are first of all try to understand how the, you can say, energy is going to affect the periodic motion, because the graph is little bit different as compared to the normal energy graph. Okay, but the concept is going to remain same, which says that, let us start for part A. And we know that the total energy of a particle, which is, we can say, taken as E in this case. 1 second. Yeah, so total energy is taken as E as mentioned here. So this E will be equal to kinetic energy plus potential energy. Okay, and the equation for the potential energy is given as V of x. So we can write, so here we can say, but the potential energy PE is given as V of x, and therefore we can write that E will be equal to kinetic energy plus V of x, and the kinetic energy is given by expression that is half mv square, where v is the velocity. We can say the kinetic energy will be given as half mv square, and this will be always a non-negative value. This will be always a non-negative. So we are given that the potential energy is represented as V of x. So therefore we can say that V of x is the potential energy of the system, and this V of x is given as alpha x raised to power 4. V of x is given as alpha x raised to power 4. and it is said for the small displacement. Okay, for small x, and for small x the potential energy increases rapidly as you can say x moves away from the origin. So this is clearly from the graph. As x is going to move away from the origin, there is sharp increase in the potential energy, that is V of x. So we can say for small x, potential energy increases rapidly as x moves away from the origin, away from the origin. So from here we can also say that Vx and this Vx you can say reaches a constant value when this x becomes greater than or equal to x naught. So you can say Vx reaches out to a constant value V naught for x greater than or equal to x naught. Sorry, this is capital X naught, where the potential no longer exists, where potential no longer exists. So it means after this condition the particle has a tendency that it can escape from the, you can say, infinity. So from here we can say thus the particle can escape to infinity. But if you want that actually this particle should be executing SHM, that it should oscillate back and forth without escaping to the infinity. You can say from here, but the particle should exhibit SHM, that is it should oscillate back and forth without escaping, So let's find out what will be the condition for the SHM. The condition for oscillatory motion. Condition for oscillatory motion, and the total energy should be able to satisfy two conditions for the oscillatory motion. The total energy E must satisfy two conditions. First condition, that energy must be positive. Energy must be positive, or we can say A should be greater than 0. So it means the particle, to have a kinetic energy, we need E should be greater than equal to 0. So from here we can say that for particle, to have kinetic energy, we need E greater than 0. So it means that if E is less than equal to 0, the particle cannot oscillate. So it means if E is less than equal to 0, the particle cannot oscillate. So we can explain this two condition. So here first condition is that E is equal to 0, or we can say the energy is 0. So which basically means that particle is at rest. Okay, at some point, at any point, at some point, that is, it is unable to move back and forth. That is, unable to move back and forth. So if the particle is not moving back and forth, it is not executing SHM. Okay. Second, when energy is less than 0, and which is a unphysical thing for this entire system, as both potential energy as well as kinetic energy are non-negative. You can see which is unphysical for this system as potential energy as kinetic energy are non-negative. Okay. So therefore we concluded that at least energy cannot be less than equal to 0. It has to be greater than 0 from this discussion. So therefore we can say that thus E greater than 0 ensures that the particle has enough kinetic energy to execute SHM. So we are at least able to find out one value of E, that at least E has to be greater than 0. Okay. And so there are now two possibilities. This is not a possible because E cannot be less than 0. So this is one of the possibility, this is another possibility, and this doesn't contain any E is greater than 0, so this cannot be one of the answer. So we have only B and C options that we have to verify. So we already verified that B is one of the possible answer. Now we have to check about the relationship of E with the V naught. Okay, and V naught is you can say constant potential energy. So like we said, that energy must not exceed the potential barrier, that E should be less than equal to V naught. You can say that energy must not exceed potential barrier so E should be less than equal to V naught. So we can say that if the potential has enough energy, if the particle has enough energy, if the particle have enough energy to pass the potential barrier and escape to infinity. So we can say that the relationship E less than equal to V naught make sure that the particle is trapped within the bounded region. So which basically means that we have the bounded region which is given by minus x naught and plus x naught, and if the particle exceeds beyond this bounded region, it is going to escape to the infinity. Okay, so therefore we can say that the energy E should be less than the bounded energy, that is V naught. If it becomes greater than V naught, then the particle is going to escape to the infinity, and there will be no back and forth motion. So therefore the option number C is the correct option. So we can say therefore for the particle to perform a periodic motion, the energy E, it should be greater than 0. We just concluded from here that E should be greater than 0, and from here we concluded that E should be less than V naught. So this makes sure that the particle is inside the bounded region and able to execute the periodic motion. Okay, so in this case option C is correct. C is correct. Okay, now let us discuss the time period, which says that for a periodic motion of small amplitude A, the time period T of this particle is proportional to. Okay, so we have to find out what will be the relationship between the T. A is the amplitude, M is the mass, and your alpha is, I think, some kind of constant. Okay, so we have to find out the relationship. So for this, in order to verify the relationship or find out the relationship, we can use simply the dimensional analysis, as there is a hint also given in the question itself. Okay, it says by using the dimensional analysis. Okay, so we are going to make use of this hint that is given in the question and try to verify what is the relationship of the time period. Okay, so let us start with part B. So we say using dimensional analysis, mass M is represented as capital M and amplitude A is represented as length L, and energy is given as V of X is our V of X. So it is going to have our M L square and T minus 2. But the energy, that is V of X, is given as alpha x raised to power 4. Sorry, alpha x raised to power square. Okay. We are given that, but V of X is given as alpha x raised to power 4, and the x is our, you can say, displacement. So we can write this as alpha, and this is our length raised to power 4, and this is equal to energy. So we can equate it to the energy, that is square T minus 2. So therefore we can get that alpha will be equal to M L minus 2 and T minus 2. Now we have to find out about the time period. So we say the time period T is T, and that is directly proportional to A raised to power P, M raised to power Q, and alpha raised to power R. So we simply substitute their values, or dimensional values. So we can say this will be equal to A is our L raised to power P, and M is our mass raised to power Q, and we just calculate alpha, that is M L minus 1 T minus 1 and raised to power R. So which can be expanded as, we can write this as M raised to power Q plus R, and we have L raised to power P minus 2R, and we have T raised to power minus 2R, and this is equal to T. So now equating 1:1, we can write that Q plus R is equal to 0, P minus 2R is also equal to 0, but minus 2R is equal to 1. So with this gives us R is equal to minus 1 by 2. So if R is equal to minus 1 by 2, so from here I can say my Q will equal to 1 by 2, and my P will be equal to 1. So we got all the three values. We substitute it in the time period T, and we can say that T will be equal to proportional rather A raised to power minus 1, and we have here M raised to power 1 by 2 and R raised to power minus 1 by 2. So this can be written as 1 by A square root of M upon alpha. So we get our time period is proportional to 1 upon A square root of M upon alpha. So the options that are available to us, we can say that is equal to M upon alpha 1 upon A. So we have option number B is the correct option. Option B is correct. And now we are into the C part. in which we are supposed to find out what will be the acceleration of the particle when the value of x is beyond x naught. It means the particle is traveling towards the infinity and Vx has attained a constant value of V naught. Okay. So part C. So we have to find out for x greater than x naught, and for this condition the potential energy became constant, which gives us that V of x is equal to V naught. Okay, for this condition potential is constant, and we know that the force on the particle will be given by derivative of the potential energy. So we can say that the force on the particle, if it is given as f of x, that will equal to minus dvx upon dx, and this v of x is equal to v naught, which is a constant value. So we substitute it here, we get f of x is equal to minus derivative with respect to x and of v naught, and v naught is a constant, so it will be giving us a 0. So force beyond x greater than x naught will be equal to 0. And from here we can also say that our acceleration, if it is given as a of x, will be equal to f of x divided by mass m, which will be equal to 0. So thus for x greater than x naught, acceleration a of x is equal to 0. Therefore the options available to us is option number D is the correct option. Option D is correct. Okay. So this completes the question. Thank you.